work on all these sites. And currently we have about 5 sites that have deep wells. All the other sites have had surface exploration. So if you come to Kenya, I'll be able to take you to each of those sites that have geothermal power. And where we have deep wells is Olkaria, Eburu, Menengai, Korosi, Paka, and Sirari. So all those sites actually have a potential of 10,000 megawatts. So we have more than 10 nuclear power plants available to be connected. All we need to do is to develop the geothermal power that is available on the surface. Now, Kenya's average generation mix is actually one of the best in the world, with 91% coming from green sources, and only 9% comes from thermal sources, where we use heavy fuel oil. So 47% is actually geothermal, 30% hydro, 12% wind, and 2% solar and cogeneration. We are currently position 6 around the world in terms of geothermal power generation.
What did you do?
And we expect that in the next coming months, we will have 2 more power plants at Menengai 2 and 3, which are 35 megawatts each. And that will take us to the gigawatt club. This budget normally is very variable, but we are always either number 6, number 5, or number 7. One of those. And for your information, all that you can see in red around the world is where you have geothermal potential. So you can expect that even here in South Africa, you should be able to have geothermal power without any problem. All you need to do is to do some scientific work. Now, a very simple illustration of geothermal power, if you assume that you have a geothermal power plant on the surface and you need to capture the heat underground, all you need to do is to drill through the ground up to 3 kilometers and make sure that you case off the shallow groundwater. We don't want to pollute the groundwater. Then you capture the hot fluid, which comes all the way to the surface. Then we separate it using a cyclone separator. The steam is what we use to turn the turbines, and then the water, you take it back to the ground. So the steam goes to a steam turbine, which then rotates, and it is coupled to a generator rotor, which then produces farm power. And the power that you produce, then you need to step it up to 220,000 volts, which then you can be able to transmit over long distances. The water that you get on the surface, then you take it back into the ground. And if you do that, then you have a clean, safe, and renewable energy for generations to come. Okay? Now I'll take you through Olkaria geothermal development, because this is a premium site. KenGen owns the license for at least for 204 square kilometers. So literally, the company has a gold mine that is 204 cubic kilometers of pure gold. And they have 3 deep wells, deep drilling rigs, and we were able to drill more than 300 wells. Each of those wells costs $6 million US. So we actually spent more than 2 point something billion dollars to be able to do that. And Kenyan are pioneers of wellhead technology, and it is the home of the only geothermal spa in Africa. Now, the business model that is normally used is three-pronged. You can either have a conventional model where they use the balance sheet to finance the project, or you can have partnerships through special purpose vehicles or public-private partnerships or joint ventures or other legal entities. Or alternatively, they are able to diversify where you expand your business to generate revenues beyond traditional sources. That one you can do through green energy park, manufacturing, consultancy, and so on. Okay? Now, there are several stages of geothermal development, and one of the major stages is exploration. It is the cheapest, but the most important. It takes 3 to 6 months, but if you can do it right, you will have your project done to perfection. So, if someone is to ask me one single thing that they need to do is resource exploration and site selection. And it has to be done so well, because immediately you put a deep well inside the ground, then you will not be able to do further detailed work after that. So to me, this is the single most important step that any geothermal developer would do. Then after this will give you the first initial conceptual model. And you'll be able to do exploration, drilling, and resource assessment after you have done that. Now, the resource assessment that you do is drilling 3 exploration wells. And that will cost you 18 to 50 million US dollars. And it will take you 9 to 12 months. Now, once you have drilled those 3 exploration wells, you'll be able to get a true measure of the temperature and pressure of the reservoir. You'll be able to know the chemical characteristics of your reservoir. You'll be able to know the technology that you're going to use to generate power. And you'll be able to know whether you have enough steam to generate enough revenue to pay off your loan. After you have done that, then you can now be able to do technical and economic feasibility studies. And you will only be able to do the environmental social impact assessment after you have drilled those 3 wells. And of course, you have now to get the permits. You need to get the generation permit. You need to get the environmental permit. You also need to get a social license. A social license. This is where your community must work with you, because geothermal is always in areas where there are communities, either remote communities. So you have to discuss, sit down with them, and agree on how you are going to develop your geothermal resource. After that, the rest is easy. Then you can just go to the bank and get the money. Okay, here you need to make a very serious strategic decision. Do you want to buy your own rig, or do you want to get a contractor to do the drilling for you? If you get a company like Great Wall Drilling Company of China, they will charge you something like $6 million US. But they will be able to do the well for you in 2 months or even 1 month. So you have to do a cost-benefit analysis to be able to decide whether you want to buy your own rig or you want to contract out. Once you have done that, then you'll be able to get your geothermal conceptual model. And that's the most important in this particular case. Now, the rest is easy because from there on, you just need to get your board approval to get the money that you need to drill all the wells. And in this particular case, you need to drill, even you have a 140 megawatts and your average output is 5 megawatts, then you need 43 wells, 34 production wells, 7 reinjection wells, hot reinjection wells, and 2 cold reinjection wells. And that's where I mentioned you have to make a strategic decision. Do you want to buy your own rigs or do you want to contract other rigs? The field development, that one is easy because all you need is a contractor who has experience in high temperature and high pressure steam gathering system. The rest, you have an EPC contractor, then you have the power plant, mechanical, electromechanical supplier, then you go to the substation and transmission line, and then the local infrastructure. Now, an example is the 280 megawatts. I love this tempo because this is the easiest way of getting your contract done. All you need to do is to break down the contract. You have the steam gathering system, you have the substation and transmission line, the power plant construction, the consultancy and administration, then you have local infrastructure, and you have done the drilling of your wells. So if the government can give you the money to drill the wells, then all these other guys will be able to come on board and you'll be able to deliver a very cheap power or energy, 7 US cents per kilowatt hour. But it requires cross-continental collaboration in both engineering and financing. For Kenya, by the way, this is one of the power plants. This is one of the power plants. So if you get a chance of going to Orkaria, this is Orkaria 1, Unit 4 and 5. We added an extra unit here, so you'll get Orkaria 1, 4, 5, and 6. We normally say it's just like this complex. So you have several lecture rooms. You have Ruby, you have Emerald, you have Diamond. So it is the same way. So you have one big power plant, but inside you have different units. And you'll be able to succeed with a lot of ease. This is what I mentioned, that we drilled from 1950 to present, and we have drilled more than 319 wells. Now, one major challenge for geothermal is the initial cost, because you need to drill several wells, at least 40 wells, before you can have a 140 megawatt power plant. But if you get wells that have a very high output, then you drill less wells. So it is very important for you to do a proper scientific study so that you can cite and get the best large wells. A very good example, our top producers were 38, 18 megawatts, were 52, 18.8, were 921, 30 megawatts. So we saved the project $54 million US. If I was working for a private company by this time, I would have retired at 50, because I would have been given 10% as my bonus. Okay. Our geothermal growth, you have Orcaria 1 from 45 megawatts. Then we went to Orcaria 2, 105. Then here in between, we also have Orcaria 3, but it is owned and operated by OMAT, an independent power producer. Then we also did Orcaria 4 and the additional units with 300 megawatts. We also did some wellheads, small power plants, 5 megawatts, 6 megawatts, equal to 83.3 megawatts. Then Orcaria 5, 172. Then Orcaria 1, additional unit, 86 megawatts. And so you can see, you can be able to incrementally increase the output as you develop your resource. This is the wellhead. So you can get early generation in terms of power and revenue. It costs only $10 million US, and it is very quick to install. It will take around 6 months. We have had a lot of collaboration with other countries in the region. We believe in lighting as many candles as possible. And we have done work in Ethiopia, Comoros, Sudan, Rwanda, Burundi, and others. And Kengen has a center of excellence. So if someone wants to get scientists and engineers for training, you can always engage Kengen and they will be able to take up the students. They can also offer geoscientific services, drilling services, reservoir management, and power plant operations and maintenance. These are some of their contracts from other countries, Ethiopia, Djibouti, and even locally. So it is something that is an ongoing process, and we encourage other African countries to do so. Now, conclusions and recommendations. Number one, comprehensive capacity building for your core team of scientists and engineers. I can't emphasize enough why this is important, because that is what will determine your success or failure of your project. Then number two, intensive service exploration. You need to have a grid of 500 meters by 500 meters and data interpretation. So if you need people to do peer review, then you look for experts with more than 25 years through a scientific and technical review meeting. So if you have a scientific and technical review meeting between yourselves and others, then you'll be able to get the right output. Then the drilling contractor. That is very, very important, because if you get the wrong contractor, he will not be able to drill the well. He won't be able to drill the well. He will get challenges which are normal, but the contractor will think that they are insurmountable challenges. So you need someone with enough experience. Then of course the steam field contractor, you may need to get someone who has experience in high temperature and pressure. And then number 6, your initial power plant units should be sourced but from experienced OEMs. Make sure that the OEM has existing power plants so that he has enough experience to manage the operations and maintenance. And you must make sure that you also get framework contracts for strategic spares. Special thanks to Kengen and to the Guangzhou Institute of Science, Energy Conversion, and the Chinese Academy of Sciences. And I had a small operation about 3 weeks ago, and I realized that I need to prepare a guidebook for current and future generations. So if you are willing to support that project, you can always be able to use those account numbers. And before Christmas, you get your free copy of your guidebook. Thank you very much.
Thank you for sharing your vast experience. Can I ask one question? Yes, as you might know, I was intrigued by what you said as a big, how to say, you need to tackle sitting down with your community and make sure that they are involved in the development of the plant. You might know that in our premises in Belgium, we also have a geothermal plant, and there we sit together a lot with the community, but we have a challenge of seismic activity based on the injection. I was wondering if you ever met this challenge, which of course concerns people.
You can have a micro-seismic activity, but to tell you the truth, unless you do a background, that's why I say it is very, very important that before you start the project, you do a thorough exploration program. Because maybe it was background seismic activity. So you have to be able to prove that they existed before your project. Otherwise, then you have to be able to manage how your new activities have actually affected the community.
Okay, thank you for this advice.
Yeah.
Thank you very much. Okay.
Yes.
Yeah, thank you for your nice presentation,
Yes.
Mr. Cyrus. I saw in your video there's a introduction of the power generation by the geothermal energy. Can you introduce what's the name of the technology?
That is double flash. Let's see whether I can be able to get it where it is. That one?
Yes.
Okay. Now you can ask me.
Yes. What's the advantage of this technology?
The advantage of this particular technology is that it is very efficient and very easy to apply. It is the technology that has been used over the years for the last literally 70 years. The first geothermal power plant was in Italy from 1950 something, around 1957 or 1958. So this is the technology that has been used over time. We have only improved on the efficiency of the turbine. So from the first power plant, or Carrier 1, was consuming 13 kilograms per second per megawatt. But by the last unit, we were now consuming 6 kilograms per second per megawatt. So literally it has improved almost 100%. Okay? Yes. So,
Mr. Cyrus, if I understand correctly, you are directly utilizing underground steam, right?
yes.
There is no heat transfer between any two working fluids.
No.
So directly extracting steam from underground and
Yes.
injecting into steam turbine.
Yes.
And after condensation, you are
Putting back the water back into the yes.
Okay.
Yes.
But I think it needs a very high temperature geological formations to extract this kind of heat.
Well, if you are within the Rift Valley, you get 350 degrees in the reservoir. So it's just like your pressure cooker.
Yeah.
If you imagine your pressure cooker, if you remove the safety valve, the steam will go to the ceiling. Okay? And it is exactly the same way in a geothermal. The minute you open, the steam and water goes 500 or 200 kilometers into the sky.
I can understand, but it needs like very specific kind of aquifer, underground aquifer. Like it is not possible everywhere to extract this kind of heat. Like
No, it is not difficult. It's not difficult. It's because you know in natural state, in a natural state within the active margins within the grove, they have this steady state of steam and water, and you have heat that is coming from the magma or the cooling magmatic body. So, however long it takes, even if nothing else happens, you still have that steam available for you. So in the ground, you have either natural two-phase or compressed water, which is already waiting for you to extract. In fact, the pressure in the reservoir is around 200 bars. So when you open the valve on top, then automatically it fries.
oh, thank you. My point is like
Yeah.
this kind of quality of the heat is not available everywhere.
No, it is not available.
Yeah,
everywhere.
this is my point.
It is available within the active margins. You
Okay.
remember there was a map that I had.
I understand.
That is.
Thank you.
That is much earlier. This one. You see all these red areas around the world? This we call the ring of fire. Okay? And this is the Rift Valley running from Egypt around the Red Sea and then to the Afar region and then crossing Africa all the way to Mozambique. Okay? Then you have what we call the mid-Atlantic Ocean or the mid-rift, where you have new formation coming to the south, like in Iceland, the Azores, and others. So all those areas, you have a resource that is available for you within economic life. Okay.
Thank you. Already in deep technical discussions. I would like to have our third speaker, introduce our third speaker, which is Dr. Yisho Kyo. I hope I understand, I pronounce it a bit decently. He's an associated researcher at the Guangzhou Institute of Energy Conversion, GIEC, at the Chinese Academy of Sciences. He received his PhD in 2017 from Tsinghua University and was a visiting scholar at the University of California, Berkeley, in 2015 to 2016. From 2020 to 2022, he carried out his postdoctoral research at GIEC and joined the faculty. His research spans geothermal energy and lithium-ion battery science with a particular emphasis on thermal management, system modeling and intelligent fault diagnosis. He published over 30 peer-reviewed articles contributing to the advancement of sustainable energy conversion and storage technologies. The floor is yours.
Thank you for the introduction, Madam Chair. Okay. Good afternoon, ladies and gentlemen. I'm from GIEC, China's Academy of Science. And actually, I'm very nervous because our director is sitting here. So if I am unable to answer your question, please understand. Okay. So you already know what geothermal energy is from the previous two speakers, and I guess you also may know what heat pipe it is, but you may have never saw of the heat pipe-based geothermal energy utilization and exploitation technology. So how can heat pipe related to geothermal energy? So this is the topic I'm going to talk about. I will introduce this new technology to you. The presentation will be divided into 4 sessions. The first one is the background. So geothermal energy is green and renewable, stable and continuous. And we have found that temperature increases with steps on the Earth. If we want good quality, of the geothermal energy, we have to make use of medium, deep, or deep geothermal resources. So I will introduce something about geothermal resources in China. In China, the total per day geothermal resources is equivalent to 856 trillion tons of standard coals, which means if 2% were extracted, it can be used up to 3,000 years. And 98% of this energy has temperature higher than 75 degrees Celsius, which can be used for heating, cooling, and power generation. However, most of them are stored in the form of hot dry rock. So rather than hydrothermal resources, traditional extraction methods face significant challenge in assessing them. The geothermal utilization technologies include direct applications and indirect applications. Direct applications consist of heating, cooling, greenhouse thermal baths. Indirect applications is mainly the electricity generation. The type of applications depends on temperature and depth variations. The utilization technologies are relative material, but there exist problems such as low utilization rate. We need comprehensive utilization technology. As the geothermal heat extraction technology, they can also be divided into two classes. The wet system extract hot water from underground reservoirs for heating and other applications. They will cause many problems such as secondary environmental pollution. Indirect heat extraction technology include underground barrel pipe, downhole heat exchanger, heat pipe, etc. To extract heat deep geothermal resources, we need the technologies which only extract heat and do not take any water underground. As the main geothermal resources, the hot dry rock has no water or little water, but its temperature is high, as much as 150 degrees Celsius. People try to use enhanced geothermal systems to extract heat in hot dry rock, but it has high technical risks, such as underground well connection. Therefore, single well indirect heat extraction technology have been proposed, including coaxial tube and gravity heat pipe. So in the second part, I will talk about what is heat pipe-based technology and to exploit the energy resources in the hot dry rock. So we have to go very deep in the earth. We have to using the kilometers long gravity heat pipe. So this will make it a super long gravity heat pipe. So you may already know what heat pipe. You may already know what heat pipe it is. Heat pipe is known as the superconductor for heat transfer. It is one of the most efficient heat transfer devices known so far, which equivalent thermal conductivity is more than 1,000 times that of metal. This technology enables heat extraction without taking any water, utilization pump-free closed-loop circulation of a working medium. This design effectively avoids corrosion and scaling issues. The idea to use heat pipe to develop deep geothermal energy in hot dry rock was put forward by Professor Jiang Fangming in 2017. But the heat pipe products are normally less than 10 meters long. So if we want to use heat pipe for hydraulic heat extraction, it has to be a few kilometers long. Apparently, considerable research should be done. So in order to study the super long gravity heat pipe and its window system contain a heat pipe with length to inner diameter ratio of more than 5,000 was designed and constructed. Particular focus was placed on correlating the heat transfer performance of the heat pipe with the multi-phase flow status inside it. In parallel, we also developed a numerical model for research and development of the super long gravity heat pipe. In this model, we treat the underground part of the system as porous media. The computational domain has the two regions with different porosity and permeability values. Heat pipe is treated as a variable temperature boundary condition. Inside the heat pipe, we consider a fixed condension temperature, the fluid in the thermodynamic phase equilibrium state, and the fluid in the fully developed Darcy flow. With these tools, we constructed a comprehensive study to investigate the performance of a heat pipe system across multiple dimensions, including the structural parameters such as diameter, thickness, and internal phenomena such as the liquid of accumulation depth, also the effects of the working fluid, and as well as the impact of the external field conditions, such as the well depth and geothermal gradient. Based on these findings, we propose a guideline for the optimal working fluid selection and develop effective strategy for enhancing underground heat transfer. And we found that when the depths increase, pressure of liquid will increase. Saturation temperature of the working fluid may be higher than the temperature of the geothermal reservoir. So evaporation of the working fluid may fail. Therefore, the most important thing is to have a suitable structure. And we have proposed a specifically designed inner structure, featuring a pie-in-pie design. The super long gravity heat pipe incorporates a stacked ladder structure within the inner pipe. Now we have this new exploitation technology, the super long gravity heat pipe, and we will move on the system design of its utilization. We propose the vapor-derived dry power generation system, which can use the vapor generated from the super long gravity heat pipe to directly drive the turbine to produce electricity. This system, yes, I will show you here. The vapor generated from the heat pipe will go directly to the power generator it can remove the evaporator. So this system will have the advantage of the simple structure and less energy losses. The efficiency, we have studied the efficiency compared to other power generation systems. Compared to the coaxial tube, this the efficiency of the super long gravity heat pipe power generation system is always higher. And similar to the geothermal power generation, we propose the primary heat exchange system for geothermal heat pump system. So you see the vapor generated by the super long gravity heat pipe can be directly compressed by the compressor and then used for providing the heat we need. So, then we can use this heat for space heating. With this primary exchange system, we can remove the evaporator. So with this simple structure, and we can have a low cost and higher COP. Or it can use exactly as the traditional ground source heat pump, which use a secondary heat exchange system, just as like this one. And so, then I will introduce some successful field tests of this new technology. The first project is located in Tangshan, Hebei province of China. It features a well depth of 4,000 meters with a temperature of 150 degrees Celsius at the bottom. A 3,000 meter heat pipe composed of 2 sections with different diameters was developed using water as the working fluid. We have conducted a 4-month field test. The system successfully demonstrated stable performance. The highest temperature is can reach the 90 degrees Celsius. Its average heat extraction rate is about 190 kilowatt. This test represents the world's first successful application of a super long gravity heat pipe for medium deep geothermal heat extraction. And the second project is located in the Xiong'an new area of Hebei province, China. We utilize a 4,150 meters long heat pipe. This heat pipe was installed in the 4,500 meters deep well with a bottom temperature of 132 degrees Celsius. The heat pipe consists of 3 sections with different diameters and employs anomina as the working fluid. It was designed to serve 2 sets of tests: the heat extraction test and the power generation test. The heat extraction test shows that under average of production temperature of 37 degrees Celsius, the corresponding average heat extraction rates over the 40-day test are over 1 megawatt. The successful demonstration was reported by China Central Television. And for the I will go through quickly. For the power generation test, this system steadily generates electricity at about 7 kilowatt rate during the test. This is the longest super long gravity heat pipe up to now, and it is the first time using the vapor produced by super long gravity heat pipe to develop it to drive the power generation system. And the servo is reports a super long gravity heat pipe geothermal space heating system constructed in Taiyuan of Shanxi province, China, which has 2 heat pipes in combination with a single heat pump, so that 2 wells are located only 30 minutes apart, and the well log temperature at the bottom is around 63 Celsius for both. And so the space heating generated by this system can support around 25,000 square meters for building. This comprehensive COP can be larger than 5.5. It is the world's first super long gravity heat pipe and heat pump combined geothermal system based on the secondary heat exchanger technique. And in addition to these 3 projects we have introduced, there's 5 more projects, such as the CSIR project. This is the world's first time to adopt the primary heat exchanger technique for the super long gravity heat pipe and the heat pump combined geothermal system. And we also start to build a geothermal gravity heat pipe and solid absorption refrigeration combined geothermal system in Tangshan. So it's time to summary. Maybe I don't have too much time. I'll just go quickly. We have proposed the super long gravity heat pipe to extract Earth's deep geothermal energy. And since this system just takes the heat without taking water and does not require the pumping, so it is an innovation in the geothermal heat extraction technology. And we can use the vapor generated by the heat pump to develop it to try the geothermal utilization such as power generation or space heating. So this is also an innovation in geothermal heat utilization technology. And we have made kilometers long heat pipes, and it has successfully applied in different places in China. And this compared to the technology introduced by CSIR. This technology can be generally used in everywhere, including the hydrothermal area and the hot dry rock area and medium deep or shallow deep. Okay. This brings me to the end of my presentation. Okay, thank you.
Thank you very much. It was very clear and nice innovations. I won't go to any questions because a bit lack of time, but I assume that you can find afterwards you are prepared to answer questions if there are any. So, as the next speaker, last speaker of today, I would like to introduce Mr. Kazir Iqbal. He's also a postdoctoral researcher at GIEC, the Guangzhou Institute of Energy Conversion. And his research focuses on vapor absorption, heat pumps, pump thermal electricity storage, waste heat recovery, and multi-energy complementary systems. He has a lot of international collaborations. I won't sum them up for the sake of time. His current research focuses on the development of underground thermal energy storage solutions and the integration of geothermal energy with data center cooling and energy systems, aiming to enhance energy efficiency, grid flexibility, and carbon neutrality for digital infrastructure. Looking forward to your talk.
Thank you so much. Good afternoon, everyone. I am Kazir Iqbal, currently postdoctoral research fellow in Guangzhou Institute of Energy Conversion, Chinese Academy of Sciences. Today I am going to present an overview of geological thermal energy storage concept using corner batteries for data center cooling. So in this presentation, first of all, I will present research background, then clean energy sources in powering green data centers, and after that I will discuss an emerging role of geological thermal energy storage to reduce peak cooling demand of data center and energy cost, and finally future work. So according to data published by International Energy Agency, from 2017 to onwards, there is a sharp acceleration in data center capacity and corresponding electricity consumption. We can see from the data that in 2024, the data center capacity reached to about 100 gigawatt and electricity consumption over 400 terawatt hour. The main important driver behind this huge electricity consumption was cloud computing, online media consumption, the wider use of social media, and the rise of artificial intelligence. Traditionally, data center relies on conventional energy sources derived from fossil fuels due to their reliability, affordability, developed infrastructure, and widespread availability. However, the reliance on these finite energy sources poses energy security risks, an unsustainable cycle of energy consumption, and contribute to greenhouse emission and carbon footprints. So this glaring reality necessitates a paradigm shift towards the operation of data centers based on clean and sustainable energy alternatives. So here comes Green Data Center, which is designed with the focus on environmental sustainability. Basically, Green Data Center prioritize energy efficiency, carbon neutrality, and resource optimization. So green data centers, instead of just energy consumer, they can be energy consumer, where on the one hand they can be integrated with renewable or clean energy sources, On the other hand, they can reject waste heat to district heating network for smart city utilization, industrial processes, or even this heat can be utilized in energy storage systems, which I will discuss later on. So basically, data center is a high performance infrastructure designed to host information and communication technology equipment, including servers, storage devices, and communication devices, as well as supporting facilities such as power distribution and cooling systems, and ancillary spaces like offices and staff support areas. In data center, approximately 30% of total electricity is consumed by information and communication equipment, while nearly 45% is used by the computer room air conditioning unit, which includes chillers, humidifiers, and distribution systems such as fans and water pumps. So, the computer room air conditioning unit carefully regulates the temperature, humidity, and air quality inside a data center for the normal operation of for information and communication technology equipment. Most of the electricity consumed by information and communication technology equipment wasted as heat, which can be utilized for useful purposes. Clean energy sources in powering green data center. Currently, major part of the electricity consumed by the data center comes from burning fossil fuel, about 30%. About 25 to 27% comes from renewable energy, followed by natural gas and nuclear. When we discuss the integration of renewable energy in data center, there are 4 different strategies. The first one is on-site generation with on-site renewable energy sources. For example, we can deploy solar panels or even wind farm within the premises of data center if there is no constraints on the land availability. The second option is on-site generation with off-site renewable energy sources. For example, we can produce renewable energy source far away from the data center, such as biomass, and then transport it to the premises of data center where we can burn it in thermal power plant to generate electricity. The third one is off-site generation with off-site renewable energy, where we can produce renewable electricity far away from the data center and then supply it to data center through transmission and distribution lines. And the last one is data centers sign different power purchase agreements with third party which produce electricity from renewable energy sources and then supply to the data center. So according to the data published by International Energy Agency, there is a sharp rise in the share of renewable energy sources. And the share of renewable energy, it is anticipated that the share of renewable energy sources will be up to 42% in 2028, of which wind and solar account 25%. But the problem with wind and solar is their fluctuated nature. So here we need large scale energy storage systems for a sustainable and reliable power supply to the grid. Until now, pump hydro energy storage system is the more mature energy storage technology, followed by compressed air energy storage system. But these both technologies needs specific kind of geological conditions. Liquid air energy storage is an emerging technology, but it has typically low efficiency and high cost, whereas batteries have short lifetime and high cost. Here comes pumped thermal electricity storage system, which store electricity as a thermal energy. It has competitive round-trip efficiency and levelized cost. Here round trip efficiency means the ratio of power generation during the discharging cycle, electricity generation during the discharging cycle, and the electricity consumed during the charging cycle. So the working principle of pump thermal electricity storage system is during the charging cycle, the heat pump of the pump thermal electricity storage system consume electricity to convert it into heat and store it at a high temperature. During discharging cycle, a heat engine operates between this high temperature, hot storage and cold storage to generate electricity. Pump thermal energy storage system has different categories based on the thermodynamic cycle opted for its operation. For example, Brayton cycle pump thermal energy storage system which operates at a high temperature, for example 1000 or above. Second one is Rankine cycle pump thermal energy storage system which operates at small to medium range temperature. Rankine cycle has further two categories. Conventionally, the round trip efficiency of pump thermal electricity storage system is less than 70%. However, Rankine cycle has unique characteristic that it can integrate a low temperature external heat source during the charging or discharging cycle, which can boost its round trip efficiency equal to 100% even above. Thermally integrated pump thermal energy storage system have further two categories: hot thermally integrated pump thermal energy storage system and cold thermally integrated pump thermal energy storage system. So in hot thermally integrated pump thermal energy storage system, the vapor during the charging cycle, a vapor compression heat pump consume excessive electricity from the grid and upgrade the temperature of an external heat source, which can be from industrial processes or from data center, and store it at a high temperature. During discharging cycle, and ORC operates between this storage temperature and ambient temperature to generate electricity. In cold thermally integrated pump thermal energy storage system, during the charging cycle, a vapor compression refrigeration cycle consumes excessive electricity from the grid and cool down the storage medium at sub-ambient conditions. And during discharging cycle, an ORC operates between an external waste heat and this storage, cold storage to generate electricity. Basically, in hot thermally integrated pump thermal energy storage system, the external heat source decreases the temperature difference between evaporator and condenser of the vapor compression heat pump, thus increase the coefficient of performance of the heat pump and overall the round trip efficiency of the system. In the cold thermally integrated pump thermal energy storage system, the waste heat increases the temperature difference between evaporation and condensing of ORC to generate more electricity compared to the electricity consumed during the charging cycle. So our analysis shows that within specific working conditions, the hot thermally integrated pump thermal energy storage system can attain a round trip efficiency about 113%, whereas cold thermally integrated achieved a round trip efficiency of 107%. So the emerging role of geological thermal energy storage system in data center, reducing data center cooling demand and energy cost. In geological thermal energy storage system, within suitable sedimentary formations, heat from different heat sources such as solar, nuclear, biomass, or even using Cornet batteries which converts electricity into heat can charge geological formations such as the depleted oil and gas reservoirs. Instead of storing it into storage tanks above the surface. During discharging cycle, heat from the hot well can be extracted to deliver to power block where it generates electricity, or it can directly utilize for heating purposes. In the context of data center, this heat can be utilized to operate a vapor absorption system which produce cooling for data centers. In another scenario, cornet battery can convert cheap electricity into cooling during night and supply it to data center during day when electricity prices are high. Geological thermal energy storage can also be used as seasonal energy storage, where it can store cold ambient energy in winter and supply it to data center in summer season. So in future work, there is need of scaling thermal energy storage and geological thermal energy storage for long duration storage, where there is a need of subsurface characterization and field validations, and there is need to explore the geological thermal energy storage applications beyond data center to industrial and urban cooling needs. And last but not least, artificial intelligence driven control frameworks are needed, where we can build digital twins and predictive algorithms for real-time optimization of data center cooling needs and heating and district heating and cooling networks. We can also integrate data center within the district heating and cooling networks. So this is all about my presentation. If you have any question, you are welcome. Thank you.
Thank you very much for this presentation in another application. So very interesting and promising application.
Thank you so much.
Would like to ask if there are any questions left. Then I would be happy to end this session. It was a very concise session, I think, with very fine expertise around the table. Look forward to further deployment of geothermal energy and other applications also,
Sure.
like the data centers. So thank you very much, and also for the fine preparation of the session. The colleagues of GIEC, nice job there.
Thank you so
Thank
much.
you, and have a nice evening. It's not my field,
I think we can switch it off, no? I think we can switch it off.
Yes, so it's running from session to session, and yeah, so we have quite some expertise at our Institute of Geothermal Energy, but these people are didn't try it, so they are. I'm listening on the speakers.
Oh, I'm switching off now.
Hi,
Nice to see you again after several years. Yeah.
So now, should we leave everything? Because the current tomorrow all the